Hello. In this video, we're going to introduce a new timing measurement called Intrinsic Margin and walk through how to use it to accelerate diagnosis of timing failures in digital hardware and specifically FPGA designs. Here we have a simple timing path, and for this video, we're going to focus on performing and optimizing the setup analysis of this path. The first thing we have to do is compute the path's setup slack, which is composed of two measurements. First, we have the path's required time, which is the time for the destination clock to enter and propagate through its clock network and get to the destination register. Then we subtract from that the path's arrival time, which is the time for the source clock to enter and propagate through its clock network to get to the source register, as well as the time for the source register's data to propagate through the data path and get to the destination register. The difference between these two times is the slack. And in this case, the required time is longer than the arrival time, so the path passes setup with a positive slack. Both the arrival and required times are themselves composed of many smaller delays and constraints. Let's break them down and see what that looks like. Breaking down the required time, first we have the latch edge time, which is the time that the latching clock enters its clock network. Then we add some uncertainty, because with effects like source jitter, we may not know exactly when that edge is going to show up. Then we have the required clock delay, which is the time for the latch edge to propagate towards the destination register. And finally, there's the TSU of the register, which is the amount of time that the data has to beat the clock by for the destination register to function properly. Similarly, let's break down the arrival time into its components. We have the launch edge time and the arrival clock delay, which are analogous to the latch edge and required clock delays, but for the launching clock edge. Then we have the register's TCO, which is the time between the clock arriving and the data successfully launching at the output of the source register. And then we have the aggregation of cell delay along the path, which is the delay of the actual logic cells doing computation in this transfer, and interconnect delay, which is the total delay of wires that hook everything up on the data path. Since there are a lot of components to setup slack, if we want to improve the setup slack, we have a lot of different options. Pretty much any of these component delays are fixable if we make the appropriate changes, and changing any of these components will affect the bottom line. So commonly, the question is, well, which component am I supposed to focus on? Because it can be very tricky to narrow down exactly what the problem is, and the annoying part is that how you fix each component can vary quite dramatically. Now, before we go further, there is an important caveat here, which is that not all interconnect is created equally. Some amount of interconnect is always going to be necessary to connect the cells on a path together. Just by virtue of having elements on our path, we're going to need some wires to hook things up. So we call that necessary interconnect local interconnect, and thus the delay it incurs is local interconnect delay. Once the path is placed and routed, we may incur additional interconnect delay to actually span the distance between the cells. In this case, all the interconnect that isn't local we call fabric interconnect, and thus its delay is fabric interconnect delay. Fabric interconnect is the stuff that gets affected by congestion, place and route, and so on. In contrast, local interconnect delay behaves and optimizes more like cell delay, because the only way to get rid of local interconnect is to get rid of the cells it's connected to. This means it is useful to bucket the local IC delay with the cell delay in a term we call logic delay to differentiate it from the fabric. So coming back to our timing path, the first thing we need to do is simplify the problem a little bit by rearranging some terms. With some massaging, we can observe that there are 4 buckets that these delays fall into. First, we can pair up the clock delays and call their difference clock skew. Next, both the logic delay and fabric IC delay each get their own buckets. And finally, we can make a bucket for everything else. These delays are similar because they're defined by the SDC or controlled by how the registers have been physically implemented. These delays are more intrinsic to the path itself than the rest, and so we can identify the sum of this bucket as the path's intrinsic margin. Now the problem of improving setup slack reduces to which of these 4 buckets to focus our work on. As we'll see, fixing each bucket entails making a different set of changes to your design, and being able to focus on one bucket at a time can help accelerate timing closure. The secret to how we're going to solve this lies with intrinsic margin. Let's take a look at a different timing path, this time one that fails setup with a negative slack. First and foremost, if the path's intrinsic margin is negative, then we need to focus on improving it. Because in this case, the transfer already fails before we ever consider clock or data path delays. We shouldn't worry about those other things until we get the intrinsic margin back on track. This means adjusting STC constraints, ensuring any hard IP blocks are properly registered, and so on, in order to make sure that the transfer even has a shot of passing. If our intrinsic margin is positive, then we can check the other buckets. If we add in just the clock skew to the intrinsic margin, and the result is negative, it means the problem is our required and arrival clock delays. This check shows that the path is already failing without any component of its data path, and those cells and wires are only going to make things worse from here. Since the clock skew is so high, we know to focus on just getting the clocks routed properly. This means resizing the clock regions or potentially redesigning cross-clock transfers to minimize this skew. Next, if intrinsic margin minus logic delay is negative, then we know to focus on the cells, because even without any wires on the data or clock paths, we're already failing. So in this case, we should focus on restructuring our design to reduce the logic levels or add pipeline stages to the path, or unblock register retiming optimization. And finally, if intrinsic margin minus fabric interconnect delay is negative, then just wiring everything up on the data path is causing us to fail, and we know to focus on reducing congestion, adjusting our floor plan, or improving clustering density. So that leaves us with a pretty clean checklist. We have these 4 cases, and given a path that fails setup, we can check if the intrinsic margin itself is negative, or if intrinsic margin combined with each other component is negative. Anytime any one of these checks succeeds, it's directly suggesting which component we should focus our work on. Obviously, multiple of these conditions may apply, and if that happens, we can be confident that they all need to be addressed. Every component is being measured independently of the other components, and so we can identify that if, for example, both the fabric interconnect and clock skew are a problem, we have to fix both in order to get this setup transfer passing. And of course, it's possible that none of these conditions apply, that no individual component is enough to cause that path to fail setup. In that case, we just focus on whichever value is the smallest, because that suggests which optimizations will get us the biggest bang for our buck. Now, let's take a look at how Quartus reports on intrinsic margin. The first thing we can do is use report timing and add this extra info all argument to break down the intrinsic margin of a path into its components. We see that there are 2 different ways to compute intrinsic margin, either by starting with the slack and working backwards by removing the non-intrinsic components, or just summing up all the intrinsic components directly. Then, going through the 4 cases is a simple matter of comparing rows in this table. For case number 1, we can see right away that path B has a negative intrinsic margin. So without even looking at all the other components, we know that the path is failing by construction. Looking down at the by intrinsic section, we can see, wow, there's a 3 nanosecond clock uncertainty here, and the clock edge relationship leaves only 1 picosecond between the latch and launch clock edges. We don't have to worry about the non-intrinsic components necessarily because path B's SDC constraints are already enough to cause it to fail setup. On the other hand, path A's intrinsic margin is pretty positive, so we need to drill deeper. For case number 2, we can compare the clock skew line and the intrinsic margin line and see that the clock skew on path A is not going to be significant enough to cause it to fail, and so we can move on. For case number 3, we can take the sum of the cell and local IC delays, and in this case, both paths must be simple register-to-register transfers because there's no cell delay at all on either of them. The local interconnect delay on path A is also pretty small, so we know we're okay there. Finally, for case number 4, we can see why path A is failing. There is a substantial fabric interconnect delay, especially as compared to its intrinsic margin. We know right away that we need to focus on whatever is introducing that fabric interconnect. In addition, the Quartus Pro Design Assistant includes DRC checks to automatically do this triage for you. These checks look at the top failing paths in your design and automatically do those 4 comparisons and then report on the results. We can see that there are 6 paths in this design which have a negative intrinsic margin like path B, And there are actually two paths that have a fabric interconnect problem like path A. These checks make it easier to get the triage work out of the way and help you get down to the business of optimization. Thank you for watching this video, and I hope you find Intrinsic Margin useful.